间太多爱恨情仇，不是你我能左右。这样的相逢是不是今生负那前生的约定？我无法给你心碎的完美，总是虚伪，总是默默流泪。要怎样才不会把真情违背？不会让你看见我喝醉。这尘世间太多。
How to get Sing CSV of 5x Gantry robot. The mechanism structure of this machine is designed and manufactured at the factory. After design, they provide the IGS file of the structure. After we get the IGS file, we have to use SolidWorks to adopt the IGS file into SolidWorks and save each components of the mechanism as a start.prt file. We started from the folder d:\gac14 and to get the file provided by the factory, the IGS file. The factory gives gac14.igs, so we have to use open the IGS file function, and the SolidWorks will translate the IGS data into the system. At last, display the model on the screen. We can see the whole structure of the machine is provided, including the components. Manufactured. So we have to remove these components, which has no relationship with the mechanism structure. After picked, we have to push the delete button of the keyboard to delete all. Then we have to save the file as a assembly file .asm with the same name gac14 and save. Review the drawing. You can see the RGB arrow are drawn on the two original points. The two original points is the intersection lines of the rotating C-axis and the rotating B-axis. The intersection points at here. Right now, we have to separate all the components driven by the different axes of the motion control car. We started from the foundation and use the foundation as an example. The rest we can do following the same procedure to separate the Y component, X component, Z component, C component, B component, tool, and RGB arrows. How to do it? We just use the mouse, the cursor, press the left button of the mouse, so this one is Y7153. The second element. And this one is the first one. And this one is the third. This is the fourth. The front fours belong to the foundation. So we remove the rest of the items and left the fourth. We pick one and move the mouse cursor to the last one. Before press the left button of the mouse, we have to press Shift key of the keyboard to select all, and press the delete key of the keyboard and say yes to delete all, and the left four items of the construction. We change the color of this truss, put the cursor on top of it, and press the left button of the mouse and choose Odd Looking and pick this one. Suppose we use the green color. For a better looking for everything, so we give a artificial red number 55 and the blue level 55 and the green level 255 and say yes. After changing the color, we have to save another file name of these foundation elements. The style parts.prt. The name of the foundation we give H14. Thereafter, H14.prt are created. And then we output another file, another IGS file, and with H14 as well. So after this, we close the file to clean the screen and open GAC14 record last time. And then remove the foundation first. If wrong, just close the file and reopen GAC14 and delete the first 4 of the foundation. Right now we can save the old file, save all. Then we can do the Y component. We can use the faster way to do it. Choose this one and press the left button started from these points and continue press the left button to these points and release the button. We will mark like this and press delete key and delete all. These 3 items belong to the Y component. Then we change color. Use the same items last time. Artificial number 55, 255 for green and 55 for blue. So the Y component color changed. Then we save another file, the style.prt, and give the name y14.prt, and then save another file .igs, the file name y14, to get the y14.igs. So use the same way to separate the X component. The X is on the top of Y axis, and to get S14 IGS, and on top of the X components is Z. Then we get Z14 IGS. Beneath Z14, we separate the C component and to save C14 IGS. Beneath C14, we separate the B components only and to save B14 IGS. And then the same, we get the pure tool and save the IGS file as tool14.igs. As to the RGB arrows, the same, we can get XAR14 IGS for X-axis arrow, and to get YAR14.igs for Y-axis green arrow, and to get ZAR14.igs to get the blue arrow of the Z-axis. After these elements, the components of the different moving axes, after all these IGS developed, we can release SolidWorks and go to polychance. We started from the foundations as an example. The rest just follow the same procedure. The first things we have to use translate functions and to choose import 3D geometry. Because it is IGS file, we have choose IGS V 5.3 via a Kino ASCII file. And to change the file folder to DGAC14. So started from the foundation H14 IGS, open the file. If XYZ coordinate, just the XYZ, this one should be picked. Flip model so that the y-axis is up. Okay. Yes. Start Scene Optimizer. Start. Yes. We get the geometry of the foundation on the screen of Polytrans H14. The same, we have to export 3D geometry as DirectX file. Output a positive normal direction first. Okay. The folder is not correct, so we have to change to D14. And the positive of H14, we give the name H14A. Save it. And then we have saved negative normal direction. Export 3D geometry as DirectX file. The negative X file, we have to pick reverse orientation of all polygons and the normals, and pick flip polygon normals. Okay. And save the name as H14B. After A and B of H14 created, we have to combine H14A and H14B, the positive and the negative X file. How to do it? First of all, we have to reset scene and save nothing to clean the buffer of the display. And then import 3D geometry of the DirectX file to correct the file folder DGAC14. H14A, the positive first, in. Okay, yes. H14A on the screen now. Then we import 3D geometry of the DirectX file and import H14B, the negative of the foundation X file. Yes. So H14A and H14B all together on the screen. Right now, we export 3D geometry with DirectX file. Positive only. Okay. And save the name, original name, H14. And H14.x could be created on the file folder. The same, we reset the scene. And import IGS file of the one just on top of the foundation, which is Y14 IGS. After this, we have to export as file the positive as Y14A and save the negative Y14BX and clean the screen and import the 3D X file Y14A and Y14B, and as these two on the screen, then we have to export 3D X file as Y14. The same we can get the Z14X, and we can get the B14.X, the C14.X, and the B14.X as well, and the Tool14.X. RGB we can get XAR14.X, and we can get Y14 AR, YAR14X.X, and ZAR14.X as well. After all these X file created, then we have to copy ZAR14.X, YAR14.X, XAR14.X, Tool14.X, B14.X, C14.X, Z14.X, Y14.X, X14.X, and the last one is H14.X, and copy into CMS GAC data file. That means the data position of CAPP GAC CMS CAPP program to fill in CSV file. Now we continue to do the filling of the CSV file. We have to open CMS GAC and the data and find the old one, previous use GAC, and the copy one, rename it as GAC 14, and change every items inside according to the new data, new file name, and we survey the foundation. We took the same H14.X, so no change. The mesh 0, the foundation object 0, attached to 0. That means attached to nothing. So H14.X is a fixed component. The Y14.X on top of H14. The mesh number 1, the object number 1. The object number 1 attached to object 0. That means Y component is on the top of the foundation H. The X14.X is S component. X file with the mesh number 2 and then the object number 2. Object number 2 is attached to object number 1. So x-axis is on the top of y component. The z component, z14.x, give a mesh number 3 and object number 3. Object number 3 attached to object number 2. The z component 3 is on top of x component object 2. The c component c14 give the mesh number 4, object number 4. Object number 4 attached to object number 3. C component is on the top of z component. The b component b14.x give the mesh number 5, object number 5. Object number 5 on top attached to object number 4. The b is the children of c component. This is the limitation. And then tool 14 give the mesh number in sequence 11. The object number 11. Object number 11 attached to object 5. The tool 14 is on top of the b component. The red arrow X for x-axis SAR 14.x. The mesh number is 12. The object number 12 as well. The object number 12 attached to object number 5. The same YAR 14, mesh 13, object 13 attached to object 5. ZAR 14 dot x, mesh 14, object 14. Object 14 attached to object 5. So after these statements, the X file and the hierarchy structure, which one is parent, which one is children, are defined. The last one, we're talking about the virtual machine and the physical machine. The relationship according to the axis of the motion control car. According to ITRI's motion control car, the first axis we call it X, the second is Y, the third is Z axis, and RGB, XYZ RGB. According to this relationship, the first one, Y component on top of foundation, we give the axis number 2 according to the definition of ITRI MCCL. It is Y translation movements. Then we have to state how to define the rest items of Y component. To see here, F column translotate. That means if the parameter 1 state the Y component is a translation movement. Suppose in here, the C component transrotate is 2. That means this is a rotation element. Traditional only 0, 1, 2. 0 is a fixed component. 1, translation movements. 2, rotation movements. But why here is 3, 4, 5, 6, 7, 8? We use these items to record, to define artificially. Suppose the transrotate 3 means this is the tool definitions. So we can use S pivot, Y pivot, Z pivot, N1, N2, N3 as the most important 3 matrix transformations of the tool. And the transrotate, if marked 4, that means the first axis of the motion control cars limitation. The 5, the same, is the second axis movement limitation. So this is first, second, third, fourth, fifth axis, the positive limitation and the negative limitation. The 7 is fourth, is B axis limitation. The positive is 91. The negative is minus 91 degrees of B elements. The transrotate A is C components. 514 positive is 1.5 turn in degree, and the negative is minus 540, 1.5 turns of C elements. We go back to C. The X14, we use the motion control car 1, the X axis as X axis. The transrotate is 1. So S pivot, Y pivot, Z pivot will never used. You can feed in 0 or any number you wish. And the rotating movements, the vector is N1, 1, N2, 0, N3, 0. 1, 0, 1 is positive X direction. So the axis 1 driven X components. The Z14 is a translation. The moving direction is 0, 0, 1, is Z direction. And use ITRI motion number, the third motion axis, which is Z axis. And talking about the fourth axis, the transrotate is 2. The rotating axis is N1, 0, N2, 1, N3, 0, 0, 1, 0. The rotating around y-axis. The axis rotating around the y-axis, what we call B component. The most important of the rotating elements we have defined S pivot, Y pivot, Z pivot points. How to get these 3 numbers? If the axis rotating around the y-axis, the y elements could lead to any number you want. So we have to find S and Z pivot point. So we go back to the SolidWorks to find the B components rotating pivot points. Close the file. No saving. And open assembly vacuum file. Right now we have to find the B rotating position. We try insert the Y arrow. The Y arrow, the name of the Y arrow we see the AR14 is the Y arrow, and put it at its original position. And to see the center of it, and press the left button as the H orange round circle appeared. The center of this point is 00245.3. Why we choose this? Because the RGB arrow are located on the two original points. The G arrow indicate the rotating axis of B elements. So this is the pivot points of B elements. We go back to C. On CSV file. It seems different in here. We just say the B elements, we forget the Y coordinate. So only the X and the Z is very important. The S is 0. The Z is 245.3. So we feed in here X 0, Z pivot 245.3. So this is the B component. And the C components rotating around 001, around Z axis. And the center still the same as is this point. If this C axis rotating around the Z axis, then we don't care about the Z pivot value, which could be anything. We have to find S pivot, Y pivot points. Right now, 0, according to the record on here, is X0, Y0. So we get all of it. We use dummy.x as the limitations definition. Just we have talked. The 4 is the first axis, is x-axis. The positive is 1684 millimeter. The negative is 0. In CMS CAPP control system, we have 3 ways to control the movement of the limitation. The first one stated in here, we have seen. The second one is defined by the motion control car. During the running of CMS CAPP, you can use the definition of the mechanism to define the hardware limitation of positive x and negative x and the rest of the axis as well. The third method to control the limitation is use the hardware sensor of limitation for all the axes on the machine. As the movements touch the limitation, the controller will stop the movements immediately. By means of these 3 control of limitation, it is very safe to run the machine. After the file GAC 14 filling, then we can adopt in our system to see, to check if anything wrong in between. If nothing wrong, then the machine is defined. Before we leave the CSV table, we have to see the continue. The last item is 6. The item for 6-axis robot is 2. Right now it's 6. This means this style of mechanism, 5-axis Gantry robot, we call it 6. Then we save it. Yes. And close it. Yes. Save it. Yes. Yes. After save it, then we go back to our program to use sync input to see and to check the CSV file is correct or not. How to do it? We use new to clean the screen and press the sync input button and to see CMS GAC data. The last one, GAC 14, and open this file to see if the whole geometry appeared on the screen. If the answer is yes, that means the X file all in the CSV file. And then we have to check the parent and the children's relationship. by means of the teach menu. The first one for X movements. Press the button here. Each press increasing 10. Right now 110, and the dynamic join will reflect the correct position just in here. You can see the movements along x-axis. The parent of X component, the Y and the foundation, no movement. The children Z, C, B, tool, and the 3 arrows follow the X component movements. And we check the Y component. The Y component is the parent of X, Z, C, B, tool, and the arrows. Which parent foundation, no movements. The children follow. So it is correct. And for Z, go down because it's only 15. So we can see the parent of Z, that means the foundation Y and the X component, no movements. Only the children of the Z, C, B, tool, and the arrows follow. It is correct. And then for the force coordinate rotating around the B-axis, only the children of the B, that means the tool and the arrows following. To check the C components, the C components moving, only its children B, tool, and arrows are follow. So the hierarchy structure definition are correct. And the relationship of a physical machine and the virtual machine, it seems okay as well. Because for the first one, its translation move along the positive x-axis. It is correct. For x, y, z, and the rotation, the B and the C rotating axis, it seems moving correct. So the CSV table check finished.